We now return to body equilibrium and focus on three-dimensional problems. We again need to begin by discussing different support options for three-dimensional bodies. Some of these supports will be familiar from our earlier discussions. If we have a frictionless surface, translation is not impeded in the plane of the surface, and there is just a single reaction force normal to the surface. A ball and socket joint permits all rotations, but does not allow the ball to move through the socket, so all translations are prevented. For this reason, we have three reaction force components. A rough surface does not prevent translation in the plane of the surface, but it does offer resistance to movement along the surface, and so it also has three force reaction components. One normal to the surface, and the two associated with frictional resistance in the plane of the surface. Even though the nature of the force components differs between the ball and socket and the rough surface, the number of reaction force components is the same. A pin is familiar by now from our two-dimensional problems. Given the coordinate system shown in this figure, we would be accustomed to looking at the pin as a projection in the YZ plane. In that case, we would see RY and RZ reaction force components, but no others. But from a three-dimensional perspective, the structure of the pin is more apparent. The pin itself is mounted in bearings within a flanged support that is rigidly attached to some kind of foundation. The only degree of freedom permitted is rotation about the pin, so the only reaction component not present is a moment about the pin's axis. In this case, there is no moment reaction about X. We can't pull the pin through the flanges, so there is an Rx component, and we can't bend the pin about axes normal to its length, so there are My and Mz components. The hinge has a different look from the pin, but it permits the same motion. Its flanges are screwed into two different surfaces, permitting only relative rotation of the surfaces along the hinged axis. It has the same reaction components in three dimensions as the pin. Bearings are more complicated forms of support, in part because there are a wide variety of bearings admitting different motions. This means the reaction components associated with bearings will vary from one bearing type to another. The common denominator among bearings is that they support cylindrical shafts intended to rotate within their housings. But how they do that varies with the bearing design. In this middle row, which is a kind of plain vanilla bearing, the shaft is assumed to be allowed to slide along its axis without resistance. In this case, there are 2 degrees of freedom permitted, translation along the shaft axis as well as rotation about that axis. In this case, there is no Rx or Mx component. The other 4 degrees of freedom are prevented, so there are 4 reaction components, 2 forces and 2 moments normal to the shaft axis. In fact, if you look again at the pin support, which was also mounted in bearings, you'll notice that these reaction components are nearly identical to those associated with the pin. The difference is that we don't permit the pin to slide through the flanges, so there is also a force component along the pin's axis. Occasionally in our problem statements, you will see a bearing described as a thrust bearing. This means there is an additional component to the bearing that prevents translation along the axis of the shaft. In that case, there is no difference in reaction components between a thrust bearing and a pin. There is another important kind of bearing called a journal bearing or a self-aligning bearing, but we'll get to that in a minute. Finally, in the bottom row, we have a built-in or clamp support in 3 dimensions, which is the most rigid type of support available. In this case, we have the full complement of reaction components, 3 forces and 3 moments, because no motion of any kind is permitted. This brief video shows more clearly the degrees of freedom that are prevented and permitted in a standard plain vanilla kind of bearing. We aren't permitted to pull the shaft through its bearings, so we have force reaction components normal to the shaft axis, in this case Ry and Rz components. It is free to slide along its axis, so there is no Rx component. We also typically can't bend the shaft, so there will be moment reactions normal to the shaft axis, in this case My and Mz components, but the bearing is built to permit the shaft to rotate about its own axis, and we can see that here, and Mx is 0. The journal bearing, or self-aligning bearing, is one we will frequently encounter in our problems. It is a kind of bearing within a bearing that permits small rotations normal to the axis of the shaft. It is easy to see why this would be an important feature to have in a bearing. If we designed a system with several bearings spaced along the axis of a long shaft, and some small perturbation to the system caused the bearings to become misaligned, we would run the risk of the shafts binding within the bearings, preventing rotation and producing a functional failure of the system. By employing bearings within bearings, we are able to tolerate small departures from perfect alignment without compromising the integrity of our system. These kinds of bearings make our systems robust. This brief video contrasts the behavior of a self-aligning bearing with a standard bearing. The small rotations permitted normal to the shaft means we don't have moment reactions normal to the bearing shaft, so only two force component reactions exist. If the self-aligning bearing also has a thrust bearing, there would be three force component reactions instead. As with the traditional shaft, we can't pull it through its housing, so we have R, Y, and RZ components of force reactions. But now when we look at rotations normal to the shaft axis, you'll see that there's a little bit of play in the shaft, and that's because there's an inner bearing that's housed inside the outer bearing that allows this to happen. We can't impose arbitrarily large rotations on the shaft. If we did that, then we would get binding eventually. But the value of this kind of a bearing is that it permits these small departures from perfect alignment without causing binding of the shaft. Most of the problems we'll encounter will be assumed to have self-aligning bearings, and there is another practical reason for this. Such problems are also likely to be statically determinate. A problem involving a shaft supported by two standard bearings has 8 reaction components before any other reaction component or other unknown quantity is added to the problem. Such problems are almost always statically indeterminate. This will become apparent in one of our illustrations. Now let's look at several examples involving three-dimensional equilibrium of rigid bodies. In our first example, we have a thin rectangular plate that lies in the XY plane and is supported by a chain, a cable, and a socket or a ball and socket at point C. We have this 200-pound force acting in the minus Z direction, and we want the force supported by the chain and the cable as well as the support reactions at C. We might also mention that a chain will be like a cable in that it will only be able to support a tension and not a compression. We'll begin by drawing a free body diagram, and in this case I'll just draw the forces directly on the figure. We have a force that points from B to E, and we will express that as a tension to be determined on a unit vector that points from B to E. Similarly, for the cable, we'll have a force that points from D to E. That's a tension we have yet to determine on a unit vector that points from D to E. Finally, we have 3 force reaction components at the ball and socket joint. We don't know what direction those act in yet, but I'll just represent them and then let the algebra tell me whether we guessed correctly. So I will just represent these as positive in X, and positive in Y, and positive in Z. Now let's just note here we've got 5 unknowns. We have the 2 tensions, and we have the 3 force reaction components at the socket. In a 3-dimensional body, we have 6 degrees of freedom, so the fact that we have 5 reactions suggests that this might be a problem with partial fixity. The number of support reactions is one less than the number of equilibrium equations. Let's just keep that in mind going forward. We can see from the orientation of the cable and chain what the unit vectors are in this problem. The easier of the two is UBE because the cable lies in the XZ plane. It has a rise of 18 inches over a run of 24 inches, and that makes this a 3, 4, 5 triangle and allows us to write the unit vector from B to E is equal to minus 4/5 I plus 3/5 K. The unit vector from D to E is a little more complicated. We have now a three-dimensional orientation. We're going 4 inches backwards in X, 12 inches backwards in Y, and 18 inches up in Z. And each of those is a multiple of 2 inches, and that 2, 6, 9 run over rise is going to translate to a hypotenuse of 11 inches or 11 units and allow us to write the unit vector along DE as minus 2/11 I minus 6/11 J and plus 9/11 K. The next question is, with these 5 unknowns, what's the best way to solve this problem? We could begin by just writing our sum of the forces equals 0. That would involve all 5 unknowns. Here it's going to be easier if we begin by looking for a place to take moments that will eliminate a large number of the unknowns and allow us to solve for a smaller set of the unknowns directly. And we can do that by taking moments about C. All of the force components of C have lines of action that go through C, so they won't contribute anything to moments about C, and only the two tensions will have non-zero contributions. So I'm going to begin there. I'm going to take the sum of the moments about C and set that equal to 0. And in vector form, that's going to look like RCB cross FBE plus RCD cross FDE plus RCA cross F equals 0. Now I might also mention that in calculating moments, we talked about using a scalar approach or a vector approach. And in some instances, it might be possible in 3 dimensions to use a scalar approach, but generally speaking, once we get into 3-dimensional problems, I'm going to use a vector approach. So evaluating these one at a time, we have RCB cross FBE is equal to 24 inches in I, crossed into the tension in BE on the unit vector along BE, which is minus 4/5 I plus 3/5 K. And only the I cross K will give me a component. I cross K is actually minus J, and so this ends up giving me minus 72/5 TBE in the J direction. RCD cross FDE involves more components, so I'm going to evaluate that in matrix form. I'll pull the magnitude of TDE out here. I've got 4, 12, and 0 inches in RCD, and I have minus 2/11, minus 6/11, and 9/11 for the components of the unit vector along DE. And if I evaluate that in the I direction, I get 9 times 12 is 108/11 in I. And in the minus J direction, I have a 4 times 9 is 36. I'm going to end up with minus 36/11 J. And you'll notice the K component is 0 because we get a minus 24 minus a minus 24, which is 0. So there's no K component. And we have just this in units of inch-pounds. Finally, we have RCA cross F, and that's 24I plus 12J inches crossed into minus 200K pounds. The I cross K is a minus J. We end up with 4,800 inch-pounds in J. And the J cross K is a plus I, and that gives us minus 2,400 inch-pounds in I. So now we have these individual terms here and here and here, and we want to collect all the I, J, and K components together and force each of those scalar equations to be in equilibrium. In the I direction, we get 108 over 11 TDE minus 2,400 equals 0. And we can solve for TDE directly there, and that ends up being 244.4 pounds. In J, we have minus 36 over 11 TDE minus 72 over 5 TBE plus 4,800 equals 0. And if we solve this for TBE, since we now know TDE, we can substitute that 244.4 into this equation and solve for TBE and get that TBE is 277.8 pounds. And in the K direction, we have 0 equals 0. So let's just make a note here. This is a signature of a rigid body motion. So when we see this, if we didn't see it before, this suggests that this entire system is capable of rotating as a rigid body about the z-axis. So we'll go back and look at that after the fact. So now what's left is to solve for the socket force reactions at C. We can do this by writing our force component equations in X, Y, and Z. Each of those will end up including just one unknown, and that will be the corresponding socket reaction. In X, this is going to look like Cx minus 4/5 TBE minus 2/11 TDE equals 0. And in Y, we're going to have Cy minus 6/11 TDE equals 0. And in Z, we'll have Cz plus 3/5 TBE plus 9/11 TDE minus F equals 0. And F is, again, 200 pounds. And so if we plug in the numbers and solve for these individually, what we end up with is that Cx equals 266.7 pounds, Cy is 133.3 pounds, and Cz is minus 166.7 pounds. And what that tells us is that Cx and Cy both do point in the positive x and y directions as I represented, and the value of Cz actually goes in the opposite direction. It's actually pointing down. Now, before we leave this problem, let's go back up here and take a look at this again. We can see that because of the fact that these cables were both attached at E, and we have this socket here at C, this entire thing is capable of experiencing a rigid body rotation about the z-axis without violating its constraints. So this does in fact have a rigid body motion, its rotation about z. For the second problem, we have the same rectangular plate. It's supported by a cable, again, from D to E, and it's got the same dimensions. But now it's also supported by a bearing at point C, and it appears to be just a standard bearing. So we will represent the reaction components that way. So if I draw a free body diagram now of this, I will again have my force that goes from D to E, which will now be a different tension I'm trying to determine on that same unit vector. I know what that is. And at C, I'm going to have the ability both to rotate about the axis of that bearing, so to rotate about z and to slide along z. So I will have a Cx force component along x, and I'll have a moment reaction mx generally. I'll have a Cy component in force and an My component. So I will again have 5 unknowns, my unknown tension TDE, and these 4 component reactions at the bearing. Now we again have the question, how do we proceed? Certainly we could take moments about C again, although this is going to give us actually 3 unknowns in our equations because the moment reactions will appear. This won't give us the ability to solve as directly for tension as we did in the previous problem. In fact, the force component equations are going to be more useful here because in the z direction we have just a component due to the tension as well as the force F equals 200 pounds down. So the z component of the force vector equation will allow us to solve for the tension directly. I'll just go ahead and write the moment equation about C and the 3 force component equations, and we'll be able to see how to solve directly for what we don't know. So if we take some of the moments about C and set that equal to 0, we have our bearing moment reactions mxi plus myj plus rcd cross fde plus rca cross f equals 0. Having evaluated those last 2 terms already in the previous problem, I'll just write down the result. It turned out that we had RCD cross FE cross FDE was equal to this, and RCA cross F was equal to this. So now our moment equations in the I, J, and K directions will look like mx plus 108 over 11 TDE minus 2,400 inch-pounds equals 0. My minus 36 over 11 TDE plus 4,800 inch-pounds equals 0. And K is again 0 equals 0. Once again, we're going to have a rigid body motion in terms of rotation about z. For our force component equations, we have Cx minus 2 over 11 TDE equals 0, Cy minus 6 over 11 TDE equals 0, and 9 over 11 TDE minus F equals 0. So actually the way to proceed is to use this last equation first with F equals 200 pounds. That gives us the tension in DE, and then we can actually solve for everything else in the equations above that once we have that tension. So the result is TDE, it still turns out, is equal to 244.4 pounds. It turns out that MX is 0 inch-pounds, My is minus 4,000 inch-pounds, Cx is 44.4 pounds, and Cy is 133.3 pounds. And once again, we can see that that bearing permits rotation about the z-axis, and so this whole structure is able to undergo a rigid body rotation about that axis without violating any of its constraints. For our last example, we have again a rectangular plate that lies in the xy plane, supported by a cable and bearings at point B and C, and in part A we're asked to draw the free body diagram for the plate if both bearings are moment resisting, that is, if these are plain vanilla bearings, and that the bearing at B also is a thrust bearing. And then in part B, we're asked to draw the same free body diagram if both bearings are self-aligning. And between these two, to comment on which one is statically determinate and or statically indeterminate. First, let's get the cable out of the way. We've got a force in DE, which again is going to look like a tension in DE on a unit vector from D to E. If these are standard bearings, we won't have any forces aligned with the shaft. We will have a CY, a CZ, and then we'll have moments in those two directions. So we'll have an MY and an MZ. We'll also have a comparable set of reactions at B. So we'll have a BY, a BZ. I'll call this moment a QY and a QZ. And then the bearing at B also is a thrust bearing, so it will have a force component along the shaft. And if we look at the unknowns for this problem, for part A, we're going to have 10. We have the tension in DE. We have 4 component reactions at C. And we have 5 component reactions at B. So N equals 10 versus 6 equilibrium equations. And that's going to be a statically indeterminate problem. We've got four more reactions than we do equilibrium equations. In part B, we have the same force reactions that we have in part A, but we don't have any of the moment reactions. So we're going to have TDE, CY, CZ, BX, BY, and BZ. And so now we've got N equals 6 versus 6 equations, and we should be able to solve. So this should be statically determinate. For this reason, if we want to solve problems in statics, most of the time we're going to find that our examples assume self-aligning bearings so that these are statically determinate problems.